In this lecture, we are going to talk about numerical integration. Now, as you all know, the integral of a function f of x from a to b can be thought of as the area under the curve of f of x bounded by the vertical lines at x equal to a and x equal to b. Of course, this brings along with it the idea of the Riemann sum, which is you divide the interval up into n equal pieces where the width of each interval h is b minus a over n. You find out the value of the function at the beginning of each interval, so f of a plus h, f of a plus 2h. These are of course heights of the function at those points. Multiply them by the width h, which of course gives you the area of each of these shaded rectangles here. And after doing all this, after adding up all the individual areas, if you take the limit as n goes to infinity, the number of these intervals go to infinity, then under certain conditions this limit exists, and this limit is going to be what you call the Riemann sum definition of the integral. Now, all this is fine for a mathematics class. Of course, we would also need to worry about whether this integral exists, or do the intervals really have to be equal in size, or can we do this with unequal intervals, under what conditions can we do this, and so on. But on a computer, equal intervals of course are pretty nice, except for one problem: we cannot really take the limit of an infinite number of intervals. The computer has to deal with a finite number of quantities. This brings us to the first approximation to the integral as area. This is the Riemann sum. So this is simply whatever we had so far, h times f of a, so that area of this rectangle. Then this height is f of a plus h, so h times that is the area of this rectangle, and so on. F of a plus n minus 1 h is the height of the last rectangle, and this times h is the area of the last one. Add them all together, and if n is large enough, which means h is small enough, you would expect this to be a decent enough approximation to the area under the curve. So the limit as h goes to 0, which means n goes to infinity, is actually the exact value of the integral. If I take a large enough number of intervals, I expect this to give me a reasonably good approximation. So this is our rectangular approximation to the area under a curve, or to a definite integral. So before we proceed any further, let us try to put this to test using the Python interpreter. But before we do that, just one point: notice that we have taken f of a. I have not taken f of b. B would have been a plus nh. So because I have taken the value, the height at the beginning of each interval, I have taken f of a plus h, and so on up to f of a plus n minus 1 into h. The height of the last interval is the height of the point just before b. So let's try to see what this becomes when we use the Python interpreter to check. So I've already started the Python interpreter for you. I've also imported numpy as np, and let's start with this, and let's pick a particular function to integrate. Let's say I'm going to integrate, say, x to the 10. So first from say x equals 0 to x equals 1. So first I need to break up the interval from 0 to 1 into a large number of pieces. Let's say n pieces, and n, let's just say just 10 for the time being. So x's, the array, will be created by using the linspace function. I have to give the initial value, the final value, and the number of intervals n. I also want the step size. By the way, if I want n intervals between 0 to 1, I have to be a bit careful. Then saying n points will not give me n intervals, it will give me n points, because by default linspace returns both endpoints. Of course, that means if I specify 10 points, I will actually get 9 intervals. To get exactly 10 intervals, what I need to do is use this keyword argument. Endpoint, the argument is true by default. So by default, linspace returns both endpoints, the starting and the ending. It always returns the starting anyway, but if endpoint is set to false, then it does not return 1. Then it behaves essentially the way range does, stops short of the final value. And I am also turning on the rest step argument by setting it equal to true. This is false by default, which remember means that this linspace function is going to return a tuple, not just an array. It's going to return a tuple. The first element is the array access, the second element, or the 0th element is access, the 1th element is the step size. I'm going to unpack that array into these two variables, access and age. And just to check that my ideas here are correct, when I put endpoint equal to false, let's just take a look. Access has values 0, 0.1 up to 0.9. I've divided the interval into exactly 10 pieces, 0 to 1 interval into 10 pieces. That means each piece has a width h of 0.1, and because I have 10 pieces, the array actually has 10 elements again, but it does not end at 1, it ends at 0.9. Now the function values can be easily calculated. I need this to the power 10, so access to the power 10, and we have the y values. Now that we have the y values, what do we need to do? We need to sum them up. Just look at the formula which is peeking out from under here. All we need to do is sum up these values, and once we have the sum, we multiply it by h. So that's the rectangular approximation. Let's call that irect. So irect here is just h times, I'm going to use the numpy sum function, which in fact for this particular purpose I could have used the built-in sum function from Python, would have given you same result because we are dealing with a one-dimensional array. But anyway, we are using numpy, and sum function is more efficient in numpy, so we are using that, and that's it. So of course irect, the value comes out to be this. What should the value really be? Remember, this is x over 10 that you are integrating from 0 to 1, which means that the integral should really be 1 over 11. Is it? Just check. If I multiply this by 11, I don't get anything even close to 1. I'm getting 0.54. The error is pretty big here, right? Okay, let's see whether increasing the number of points improves things. So let's go back to the step where I calculated excess, but before that let's set n to 100. So I've increased the number of points, decreased the step size, and I'm calculating excess again. Is now a 100 element array starting at 0 and ending at 0.99. Let's calculate y's corresponding to that, and let's calculate irect again by summing up these y's, multiplying by the h now, which is of course 0.01 now. Let's see what irect works out to be. Well, it has increased quite a lot, and let's see whether multiply irect by 11, the answer should be 1. Well, not quite, but it's coming close. So what this should really convince you is that the rectangular approximation doesn't really work very well here. And of course things are improving with increasing number of intervals, but well, let's see. If I made n 1000 and done the calculation again, calculated excess, then the new y's, which is now a 1000 element array, and calculated the irect using the new y's with of course a new h, and now multiply this irect by 11. Well, now I'm getting something pretty close to 1, still 0.99, only 1% away from 1. So this is 1% away from the correct answer, and to get to that good a result I actually had to take 1000 points. So I'm pretty sure you will agree that this is not really a very accurate method. So can we do better? Well, of course we can. Before we go there, let me just introduce to you a slightly shortened notation. Instead of f of a plus ih, I'm just going to write f of I, which means f of a, which was the beginning value, becomes f0, then you have f1 up to fn minus 1. This is of course the same rectangular approximation formula in this slightly different notation. But now let's see what we can do to get a better result. And just one look at this diagram here should suggest at least one immediate improvement. After all, a lot of this green space is not being captured by my rectangles, and in fact here the rectangles are overestimating all these pink areas, and that's basically because the function f of x changes quite a lot from one end of the interval to the other end, and the rectangle whose height stays fixed will obviously miss that. So instead of doing that, what we can do is try to approximate this curve not by these flat lines here, but by straight lines joining these pieces, which of course gives us an approximation to the area under the curve by the sum of the areas of each one of these trapezoids. Of course, even here the curve is slightly either being underestimated or overestimated. Here the trapezoids actually overestimate the area under the curve. Here the curve is peeking out from under the trapezoid, so they are overestimating the curve. Rather, here the trapezoids are underestimating the area under the curve. Here the trapezoids are actually overestimating. But you should be convinced that these should give you a better approximation. For this, what do we need to do? We need the sum of the area of each one of these trapezoids, and elementary geometry tells us that the area of a trapezoid is the average of the two parallel sides times the width. So here f0 is the height here, f1 is the height here, so you take f0 plus f1 by 2, multiply by h. For the next interval, f1 and f2 are the two heights, f1 plus f2 by 2 into h. For the final one, the two heights of the two ends are fn minus 1 plus fn by 2. Notice that fn, which is f of b, is making an appearance here. It was not being used for the rectangular approximation. But if I just rewrite the whole thing, it's pretty easy to see that each one of the intermediate values f1, f2, f3 up to fn minus 1 are actually coming in twice. Once for the trapezoid on the left, again for the trapezoid on the right. So this is f1 here appears in the formula for the area of this trapezoid and the formula for this trapezoid. Similarly, f3, this height, appears in the formula for this trapezoid, also in the formula for this trapezoid. Since each time they appear with a weight of half and they appear twice, they're really just being added together. The only exception is the very first one, which comes in only once with a weight of half, and the very last one, which comes in with a weight of half. So this is the trapezoidal formula. You add up all the intermediate values, fine, So the first and the last one is added up with a weight of 0.5. All the other values are added up, of the function are added up with a weight of 1. And then of course you multiply the whole thing by h. So let's try to see what this gives us in the trapezoidal rule for our particular function. So let's go back to the interpreter. Let's go back to n, a small value, n of 10, which in case you've forgotten by now gave us a pretty bad value. If we were using the rectangular approximation, it gave us only 0.49. So I directed to 11, came out to be 0.54 instead of 1. So quite a long way off. So, but let's go back to 10 points and try the trapezoidal formula. I once again need the values of x's and h, but now I will drop the endpoints equal to false part, because I need both endpoints 0 and 1. Remember here f of a and f of b are both needed. I need the rest step equal to true to give me the size of the step. And if I really want 10 intervals, I really should be doing this. Because if to get 10 intervals with 0 and 1 both included, I actually need 11 points. So this is my x's. So once x's has been calculated, I can easily get y's by raising that to the power 10. Now of course, like x's, y's will be an 11 element array, and what we need to do is I trap the trapezoidal result. Let's see how good this is going to be. So this is h multiplied by, I want the very first value and the last value of y's, the array. So the first value is y is 0 and the very last value is y is minus 1. So I want to add them together and multiply by 0.5. So that's the fa plus fb by 2 done. And then I need to add up, so use the np.sum, all the y values except for the 0th and the last. So I need to take a slice. What slice? I need to start at element number 1, dropping the element number 0. I need to stop before element number minus 1. Remember, in the slice the notation is the same as in range. The start value is where you start, the stop value is the value before which you stop. So that's it. Of course I need to complete the bracket. This bracket here was just the argument bracket for sum. Now this bracket is putting the whole expression into a bracket so that you can multiply by h. So this is your trapezoidal formula. So let's see what I trap is coming out to be. So it's coming out to be 0.991. 0.0991, and if you multiply it by 11, notice this is supposed to be 1 over 11, and so 11 times that is supposed to give you close to 1. It's actually quite good. Even with 10 points, I'm getting 1.09, which is still around 9% away from the correct answer. But with only 10 points, I'm getting 9% away, whereas with the rectangular approximation, I was nearly halfway to the correct result. So almost 50% out. But just to check whether this was a fluke or not, let's increase n to 100 and let's calculate the whole thing again. So I'm creating the excess array again, calculating y's, that's about 10, and just to remind you, the trapezoidal formula is take half of the sum of the 0th value of the function, that is y is 0, and the f of b is the last value in the array, y is minus 1, So you have added them together, multiplied by 0.5 to get this term here, and then I've added up all the rest by taking a slice which excludes the 0th and the last elements, and then use the np dot sum function on that, and then of course multiply the whole thing by h. And let's see how good this is. If I multiply this I trap by 11, I actually get a rather amazingly good result. Is well 0.0009 away from 1, so it's well less than 1/10% away with 100 points. So you will agree that this is definitely much better than the rectangular formula. Can we do better? Of course we can. Here in the trapezoidal formula, what we had done is we had taken the area under the curve, or rather approximated the area under the curve by area of a lot of trapezoids. What that also means is that we had approximated the curve itself by straight line segments. So if you have only 2 points on a curve, the 2 endpoints of an interval, that's actually the best you can do. You just join them with a straight line. And if your 2 points are close enough and your curve is not too horribly kinky, it's going to be a pretty good approximation, which is why the trapezoidal approximation works. Of course, the trapezoidal rule will give you an exact result if the function f of x had been a linear function. Then of course the area under the curve really is a trapezoid, then you would get an exact result from the trapezoidal function, trapezoidal approximation. As you have seen, even for a function which is pretty far away from a straight line, this y equal to x over 10 curve, the trapezoidal approximation is giving a decent enough result, but you can improve upon that. How to do that? Well, the next step is what is called Simpson's one-third rule, and there what we do is, instead of joining 2 endpoints of an interval by a straight line, we take 2 successive intervals which gives us 3 points and pass a parabola through those 3 points, which should be able to follow the curve, if it is curved, better than the straight line. So I've shown this schematically here for 2 successive intervals. Just for the ease of calculation, I've taken the midpoint to be at x equal to 0, and of course that means the left hand is at minus h, the right hand is at plus h, and I've called the value of the functions at these 3 points f minus for f at minus h, f0 and f plus. So we have 3 points on the curve: minus h f minus, 0 f0 and plus h f plus. So these are the coordinates of 3 points on the curve. What we do is send a parabola passing through them. The parabola y equals a0 plus a1x plus a2x square, and then approximate the area under the curve in these 2 intervals by the area under the parabola. So how do we get the parameters a0, a1, a2? Simple. I just put in x equal to 0, x equal to minus h and x equal to plus h in succession. Putting in x equal to 0 in this formula obviously makes a1x and a2x square terms drop away, so f0 is simply a0. The parabola also passes through minus h f minus and plus h f plus, and if you put in minus h f minus, y is f minus, x is minus h, you get this, and putting in x equal to plus h and y equals f plus, you get the other equation. Because these 3 equations are 3 equations in 3 unknowns a0, a1, a2, and using them is very easy to actually calculate a0, a1, a2. In fact, a0 is just f0, and if you just added and subtracted the other 2 equations, you will immediately get a1 and a2 from the knowledge of a0 that you already have. And okay, you should be able to do the algebra yourself. In fact, you should do the algebra yourself, and you get these values a0, a1 and a2. Fine. now that you have A0, A1 and A2, by the way, the formulae for A1 and A2 should look very familiar from the last lecture, and they look exactly like the central difference formula for the derivative, first derivative, and the formula for the second derivative, A2. Expression looks like that. Just think about it a bit and you should be able to figure out why that is the case. Anyway, these are the A0, A1, A2 values. What we need is the area under the A0 plus A1x plus A2x square curve, and that's this integral, of course. It is pretty easy to see that this integral is twice A0h plus 2/3 A2h cube. The A1 term drops off because x after all is an odd function and you're integrating from minus h to plus h. And if you now just put back the values of A0 and A2, so it turns out that you don't need the value of A1 at all. You just plug them in, and once you plug them in and simplify, this is the value you get. h by 3 f plus plus 4 f0 plus f minus. So the area under the parabola is 1/3 of this weighted sum. The middle point is weighted 4 times, the two endpoints are weighted once. Of course, a quick check whether this makes sense is to see that if this were a constant curve with the same height f throughout, that is f plus, f minus and f0, where all equals to the same value f, then this would come out to be 6f in the sum here into h by 3, that's twice fh. The 2 of course comes from the fact that width of the whole region encompasses 2 intervals, so the width is 2h, so 2h into f. Now this is for just 2 intervals, but just like in the trapezoidal rule, we don't actually take the entire interval from a to b and break it up and just join AFA and BFB by a straight line to get a single trapezoid. We first break it up into many pieces and replace each piece by a trapezoid, giving us a composite trapezoidal rule, the form in which the Simpsons 1/3 rule is actually used. By the way, it's called 1/3 rule simply because of the h by 3 here. The form in which it is used is the so-called composite Simpsons rule. That's the one which we usually mean when we say Simpsons rule. So what do we do there? We break up the interval a to b into many pieces, but remember we need 2 intervals for each parabola, so we need the number of intervals to be even. So that's important. We need an even number of pieces, and we take 2 successive pieces. Let's say these have heights f0, f1, f2, and this is the area under, not really area under this part of the curve, but area under a parabola which would approximate the curve here by going through all these 3 points: AFA, a plus h, f of a plus h, and a plus 2h, f of a plus 2h. So that's the area that we get. For the next interval, of course, we get f2 plus 4, f3 plus f4. For the next one, we get f4 plus 4, f5 plus f6, and so on, until for the very end we get f2. There's an error here, of course. This is f of 2n minus 2 plus 4 f of 2n minus 1 plus f of 2n. So in the end, what we have is a final 2 points, f0 and f2n, f of a and f of b, only come in once each. The points f1, f3, f5, the ones sitting in the middle of the 2 interval pairs, which of course means the ones which are sitting at the odd positions, come only once, but with a weight of 4 every time. On the other hand, apart from the first and the last point, fa and fb, all other even point positions, f2, then f4, then f6, they come in twice with weight 1 each. So basically what happens is this formula becomes h by 3 times the first and the last value taken once, all the odd position points taken with a factor of 4, and all the even position ones taken once, well, not once but twice, The weight of 2 here comes because they occur twice each time, because f2 for example comes in when I take the first and the second interval, and then also the third and the fourth interval. f2 is at the junction, f2 comes twice. Similarly for f4, f6 and so on. So this is your final version of the composite 1/3 rule, which is usually what is called the 1/3 rule. You take the extreme points, give them a weight 1, take the odd position points, give them each a weight of 4, give them the other even position points apart from the extreme ones, give them a weight of 2, add the whole thing together and multiply by h by 3, and that's your final result. So let's see how this fares for our function x to the 10. Let's go back to n equals 10. That's a nice even number. Remember, for the Simpsons 1/3 rule to follow, to work, the composite Simpson 1/3 rule to work, you need an even number of intervals. So of course here, because I want both endpoints 0 and 1, fa and fb is needed, I will use the default behavior of linspace, which is to include both endpoints. But there I have to remember to actually add 1 to n for the number of points, because the number of intervals is what you need to be even. Thus 10, I need 11 points. I've used step equal to true again here and so on, created the array. Then of course with this I have to create the y's array, the value of the y values of f of 0, f of 0.1 and so on. Now comes I Simpson. So that's h divided by 3 point star. Now we have to be a bit careful. It's y's 0 plus y's minus 1, done, plus 4 times the sum of all the odd positioned y's, all odd index y's, 1, 3, 5, etc. And that's easy to do. All you need to do is start at 1, go on till the very end. Of course, the end here is element number 10. There are 11 points, so it starts at 0, ends at 10. I don't really need the end point, but that's fine. Or I can actually put the minus 1. I don't need that, but and then, and this is what we have not perhaps used in the last lecture on numerical differentiation. Slices, just like the range function, can also have one more argument, the step size. So here what I'm saying is, take the y's array, but take a slice of it. Start at the 1th element, drop the 0th, then go on, drop the last element. You don't really want that. Of course, that's an even positioned element, y10. I don't really want that anyway. But go in steps of 2. So this is y is 1, y is 3, y is 5, y is 7, y is 9. I take the sum of all of that by doing the 9 bit of sum, multiply that by 4, plus 2 times. Now the drill should be clear. You again take the sum, and you take y's, a proper slice, but the slice has to be start at 2, drop the last one. This is important. In the previous case, the last one would have been dropped anyway because the step size is 2. We are starting at an odd position. Here, if we had just taken a step size of 2 to keep the even ones, the last one y10 would have been included. But we don't. We drop the last one explicitly here and write this. So this is my Simpson's 1/3 rule formula. So this is only with 10 points, and let's see how good iSimp is. And the best way to check that is multiplied by 11 and see how close the result is to 1. So notice that this is actually better than 1%, in fact better than 1.5% with only 10 points. just to remind you, when we were using trapezoidal a while back, when we used 10-point trapezoidal, well, we got to within 1%. But with 10-point Simpson, we are better than a 0.5%. So the Simpson's 1/3 rule is better. Of course, Simpson's 1/3 rule would be exact if the curve y equal to fx were really just a parabola. So any quadratic curve, I would get an exact result. But this makes it approach the correct value much better. And just to show you how things improve with number of points, if I take 100 points, created the array again with 101 points, 100 intervals. And just to remind you, this is isimp is h/3 times the f of a, the 0th value of y's, f of b, the last value of y's, plus 4 times the sum of the y's at the odd positions, which is you start at 1, then you go in steps of 2. So it's 1 colon, but I could have written just 1 colon 2, that would have still worked, because I don't really have to drop the last entry here. The last entry would have automatically been dropped. But in the third piece, where I'm taking just the even ones, I actually have to explicitly drop the last term, 2 colon minus 1 colon 2. Let's try this again. Let's try how close this times 11 is to 1. Oops, something seems to have drastically gone wrong. Oh, of course it has gone wrong, because all I have done is I have recalculated the x's, but I have not calculated the y's for this array. So I'm still using the original 10 element or 11 element y's array, whereas I should have been using the 101 element y's array, which should come out of this x's. So let's calculate the y's. Using this y's, let's calculate isimp, and now let's see. Yeah, this is pretty good. In that 1, 2, 3, 4, 5, 6, 7th decimal place. So the difference is in the 7th decimal place. So the Simpson's 1/3 rule is actually pretty good. Even with 100 points, it gives you a pretty nice accurate result for a polynomial which is as high order as x to the 10. Of course, if we had tried a higher order polynomial, let's just say, let's just for the heck of it try x to the power 1000. They're pretty high order polynomial. Remember, Simpson is supposed to be exact for x is equals to, and I don't even know whether this is going to be very good. Let's give it a try. Let's calculate I Simpson for this function. And let's see, this should be, well, the answer should be 1 by 1001. So I'm multiplying this by 1001 in the hope to see how good I Simpson is. Well, this one is pretty bad. So just because the Simpson's formula worked nicely for with 100 points for x to 10, is 1000 is a long way from that. So even with 100 points, Simpson's formula is not really working that well. If I tried n equals 1000, let's say, tried it again. Of course, we have to calculate the x's first, then the y's from that, then the Simpson's formula from that. Well, that's not too bad. With 1000 points, I'm getting a 0.5% accuracy. Of course, 1000 points is not a great deal for today's computer, but if you have to do the integration over and over again, this may not be a great thing to do, because that will slow down your program quite a lot. So are there better approximations? Yes, there are. We are going to cover them in the next lecture. But before we do that, let me just show you a slightly different way of evaluating the integrals according to the trapezoidal or the Simpson's rule, which might come in handy. Just to remind you, the trapezoidal rule was that you take the first element of your function value array, that is y's for us, and last element, weight them by a factor of 0.5, add all the rest of the elements to this and multiply by the step size. So let us try doing this calculation once again for our familiar function y equal to x to the 10 and see what comes out, and see how we can do this with a slightly different twist. So let's create the access array again. Let's say our n, the number of intervals, is back at, let's say 10, let's say 100. So I want the array access to be, and the step size h out of this linspace function. So it goes from 0 to 1, and because I want n intervals, I'm putting in n plus 1, and red step equals true. Of course, I want both endpoints, that's why I'm not using the endpoints equal to false argument. So I've created my x's. The y's, the array of values of the function, can be easily calculated by raising this array to the power 10, which means, of course, every element gets raised to the power 10. And now what I need is a set of weights. As I said, I weight the first element, the 0th element of y's by 0.5, the last element, which is the minus 1 element, by 0.5, all the other elements by 1, and add them together. So let's first create an array of weights. And because most of the weights are 1 anyway, I will start with an array which has only 1s, which is exactly the same size as y's and the same data type. And an easy way of doing that is using the ones function from numpy, of course, but for that I will have to specify exactly what size I want, etc. However, because I want an array of ones which has exactly the same size and data type as y's, I will just use the ones like function. So I have a ones like y's array. If you have forgotten what this ones like function does, take a look. It has created an array of ones with exactly 101 ones, each of them a floating point, because y's had a d type of floating point, float. So this is my w's array, but this is not complete, right? I don't want to weight every element by the same amount 1. I want to weight every element other than the 0th and the minus 1th element by 1, but the 0th element and minus 1th element I want to weight by 0.5. In case you are wondering, this is a perfectly legitimate expression which sets both 0 and minus 1 element of w's, the 0th, the very first, and the 1th, and the minus 1th, the last element by 0.5, just to see whether we have done it right. Take a look at w's again. You can see that the last element is 0.5. The 0th element has crawled off screen, but here it is. So now I have a sequence of weights which are appropriate to the trapezoidal formula. So how do I use this? Simple. All I do is, if I multiply the arrays y's and w's, they get multiplied element by element, which means the 0th element of y's gets multiplied by 0.5, which is the 0th element of w's. The last element of y's gets multiplied by 0.5, all other elements get multiplied by 1. So I have created a new array in which the y's have appeared with the proper weightages. All I have to do now is just sum them together and multiply, of course, by h, and this should give me my 100 interval approximation using the trapezoidal rule for this integral, which should have come out to be 1 by 11. And I can easily check whether this result was 1 by 11 by multiplying it by 11. But well, you might wonder how we would multiply it by 11, because I have not saved the last result. I can of course bring in the last result by using the arrow key and multiplying by 11 again. But here is a trick which you may not know, but which is useful. Python interpreter allows you to access the last value by using the underscore character. So if you say underscore, it means the last result. So I just write underscore, multiply by 11. Underscore, remember, is the symbol you get from the minus key on your keyboard. You hold down the shift and you get the result, which of course we have seen before. So this is how you would do the trapezoidal sum using an array of weights instead of using slices on the Y's array. Let me also take this opportunity to introduce a new function to you, which will come in quite handy in many cases, especially involving things like linear algebra, for example. Notice that what I did a while ago was I multiplied each element of y's by each element of w's. That's what was done by the simple y star ws thing, and then we use a sum function to add them up. Now let me remind you that this kind of a thing, where you take two elements out of corresponding elements out of two arrays, multiply them together and add, is actually quite familiar to all of you, especially in mathematics and mathematical physics. Well, a1b1 plus a2b2 plus a3b3 should ring a bell. That's nothing but the dot product. And this task that we have done, multiplied each element of y's by each element of w's and added the sum together, is actually also achieved by another function which numpy supplies you with. It's called a dot function. So what we could have done is, instead of doing this, use the function np dot dot. You will see later that this comes in very handy when you do matrix multiplication and stuff like that, and give it two arguments. Remember, sum takes only one argument array, which was the product array y's and times w's. This one, on the other hand, is y's time and w's. The two arguments go into the dot function, and what dot does is returns the dot product. Of course, if I do this, I get exactly the same result. Now, whether you use the sum of y star w's or dot y's comma w's is sort of a matter of taste here, because essentially the same thing is being done internally. I just took this chance to introduce the dot function to you. You will see the dot function a lot in later applications, especially where matrix multiplications are involved. Let us now quickly tell you how to do this same thing with the Simpson rule, the Simpson one-third rule. In the Simpson one-third rule, which you can see peeking out from the bottom here, what you have is you weight the 0th and the last element of your y's array by 1, all the odd positioned elements by 4, all the even positioned elements other than the 0th and the last, which are also even positioned elements by the way, by 2, and add them all together, remembering to multiply by h by 3. So what we could do is start with a new w's array. Of course, my w's array earlier has changed, so let's go back to a w's array which has only ones to begin with. So I'm using the once-like function. I don't need to change the 0th and the minus 1th element here, they're already 1, but I do need to change every one of the odd order elements to 4. Well, that's done by easily using slicing. So start with the 1th element, you go up till the very end. Well, you can drop the last element here as I have done, but that frankly was not necessary because the last element wouldn't have been reached anyway. 1 colon minus 1 colon 2. The 2 gives you the step size. Because we are using the step size of 2, I would not have reached element number 100, which is the last element. I would have only reached up to 99 anyway. So I could either have done this, or I could have just written this. Of course, I need 2 colons to tell Python that the 2 here is a step size and not the last element. Anyway, let's write this and put this equal to 4. There's one reminder. Once wise gave us a array which is the same size and d type as wise, which means the d type of w's was float. So when I'm trying to put in the apparently an integer here, 4, into the array of course will not take that. All elements in an array have to have the same d type, which means that the 4 will be converted or floated to 4 point, and only that will go in. How do we handle the other elements, the even order place elements? Simple. Start at the 2th position, not at the 0th, and don't go up to the last one. That's why you have a -1. This -1 is mandatory, unlike the previous step where I could have dropped the -1. Here I do want to not go up to the last element and then go in steps of 2, and this I have to put equal to 2. Just take a quick look at what the arrays w's has become. It's become an array of 1, 4, 2, 4, 2, 4, 2, exactly the kind of weights that we want. So now our job is simple. All I do is I calculate either the dot or the np dot sum wise star w's, and remember that in the Simpson 1/3 formula we need to multiply by h by 3. That's where the 1/3 comes from in the name, and we get this. And just to check how good this is, it's 100 intervals Simpson's method. I'm getting a pretty decent result. This of course should not come as a surprise. I've already seen this before. In the next lecture, as promised, we are going to look at how to improve on this by looking at things called cos quadrature.